So I want to jump into the next topic. So continuing on with electromagnetism, we've got motors and generators. So we can bring everything we've looked at to see how motors and generators operate. And motors and generators are everywhere. Pretty much a lot, or like the majority of your appliances use motors and generators, whether that be for cooling fans on your computer, or whether that be for, like we looked at the washing machine example with fans and whatnot. Generators are what's used to generate electricity. We'll look at details in a second, but motors use electricity to spin things, so that turns electrical energy into mechanical energy, whereas generators use spinning things to produce electricity, so that turns mechanical energy into electrical energy. So if we sort of draw an energy diagram sort of thing, we have electrical energy, so I'm going to write EE, and that turns into mechanical energy in the case of motors. Whereas for generators, we have mechanical energy turning into electrical energy. And what I mean by that is, for example, if we're looking at these cars don't look like they're electric, but if we do have an electric car, right, what we're going to do is we're going to supply that motor with electricity, and that motor is going to use that electricity to generate a torque, and that's going to make the car go forward. So we're turning electrical energy into mechanical energy by using a battery or something to store energy and sending it to a motor, thereby turning it into mechanical energy by making the car move forward. So we've got kinetic energy. Generators, on the other hand, use spinning things to produce electricity. So for example, wind turbines, right? We've got the wind that's actually turning the turbine, right? We've got the wind producing a torque on the turbine that results in turning. So if we hook it up to a generator, that turning, right, that kinetic energy is transitioned into electrical energy. So that's what generators do. So the purpose of a motor, so looking at motors in a bit more detail, the purpose of a motor essentially is to use the motor effect to generate a force. And this force then generates a torque, and the torque is used to spin whatever appliance or whatever you need to spin. So here we have sort of a schematic of the DC motors. There are a few specific components that I want to highlight here, but in essence, we've got current that goes through to a coil, and the wires on that coil have a current flowing through it, and we've got permanent magnets on either side. And so if you think back to the motor effect slide, that's going to generate a force. And because this force is off center, that's going to generate a torque. If you think about your mechanics unit, right? Remember, if you have force applied at a distance from a pivot, then we have a torque. So this force on that conductor generates a torque, and that torque is used to spin whatever you need to spin. So DC motors consist of magnets that are set up to generate the stationary magnetic field. So that's the stator. So you have the North Pole and the South Pole, and so that's going to generate a magnetic field or a permanent magnetic field. That's called the stator for the permanent sort of non-rotating part. The current carrying coil that is free to rotate, that's called the rotor here. And you've got the split rings here, split ring commutator. So the rotor pretty much consists of the current carrying coil and the split rings, but the current carrying coil is the thing that actually holds the current, and that's the thing that experiences the force. In terms of the split ring commutator, right, that's the part that connects the coil to the external power source. So this is our external power source. So it could be, for example, a battery. Battery supplies DC. And remember, these are DC motors, so they require DC current to operate. We'll look at AC motors or AC generators in a second, but we've got DC motors here. And so we want to supply a DC current. And what that DC current does at the split ring commutator is that at this point here, it goes through this coil and around, and back through. And because it's a current carrying conductor within a magnetic field, it experiences a force. Since the force is off center, so this is the center line here, and that center line has some distance from the force there is some distance from the force to the center line, so that generates a torque, and so we can use it to spin things. The key thing here is looking at the split ring commutator. That's sort of like the part that many students get confused with. What the split ring commutator does is that it connects the coil to an external power source, and it changes the direction of the current every 180 degrees. So what that means is if we spin this around 180 degrees, right, this split ring commutator makes sure that the current direction of the current stays in the same direction. Because if we have the current changing direction every 180 degrees, the motor isn't going to spin in one continuous direction. It's going to go back and forth. It's going to sort of flicker back and forth. So what we want it to do is it goes all the way around, and so now this side is going to be on this side, and so we're going to maintain a constant direction of rotation. So how does the forces produce a torque? We did talk about that in a bit. We've got the current carrying conductor with a magnetic field, and if we use our right hand rule, we've got the magnetic field going this way, current going this way, so the force is perpendicular to our palm, so it goes downwards this way, whereas the current in this side is going back towards us. So we have the direction of the current. It's a bit hard to position my hand like that, but we've got the direction of the current, got the magnetic field, and so the force is perpendicular to that, so that way. This is called a couple, or we've got like two forces that are in opposite directions, but on either side of the axis of rotation. And so that's going to cause a torque or a couple, and that's going to generate the torque required to spin whatever we're spinning. So remember, just think back to your mechanics unit. Torque is the turning moment of a force, right? And so the distance from the turning point is, the torque is equal to the distance from the turning point, so R, times F. F is the magnitude of the force, and the sine theta is dependent on the angle between that point, that is dependent on the angle between that radial vector and the force vector. So in this case, it's 90 degrees. So that's okay. So sine theta, in this case, if theta equals 90 degrees, we have torque equals RF, because sine of 90 is 1. So in this case, it would be RF. But the reason the sine theta here is because of the fact that if we have a force, maybe I'll draw on one note just to give myself a bit more space. Just as a quick recap of your module 5, if this was our pivot point, we have force applied as so. This is our lever arm, by the way. So you have R, we have force applied and it's perpendicular to the lever arm. We have maximum torque generated. But if you think about the situation where we've got a lever arm like so, same lever arm, same distance, but this time the force is applied in the direction of the lever arm, as so. Is that going to actually generate any torque? Well, the answer to that is no. So if we have an angle of 180 degrees here, right, what happens when we have sine of 180 degrees? Well, that's 0. So the torque equals to RF sine theta, because we're only interested in the component of the force that's actually producing a torque, because anything that's parallel to this lever arm is going to not generate a torque. It's going to just, it's not going to generate anything. So we want to focus on the component that is parallel to that lever arm. So if we have a force, for example, at an angle, right, and this is our pivot point, this is our radial, this is F, this is theta. We're only interested in the component of the force that's perpendicular to that lever arm, and not the component that's parallel to that lever arm, because that parallel component is just pulling that rod. That's not going to generate any torque. Only this vertical component is. So yeah, that's why this sine theta is here. This is a side note, so you're not just blindly memorizing it. You want to make sure you understand where that sine theta comes from. Okay. Oops. Now, here's a key question. What does the commutator do? Well, this is the split ring commutator that I talked about before. What does it do? Well, it reverses the direction of the current every 180 degrees as to maintain a constant flow. So what I mean by that is, in this animation, if you have a careful look, you can see that the direction of the force is always in the same direction. Right? On the left-hand side, it's always pointing downwards. On the right-hand side, it's always pointing upwards. But if you look at the specific side of the coil, you'll see that at this point, it's on the starred side, right? At this point, it's down. At this point, it's up. This point, it's down. This point, it's up. And so what the split ring commutator does is it changes the direction of that force every 180 degrees on that specific coil as to maintain a constant direction of rotation. So the split ring commutator comes in contact with what are called the brushes. These little black things here are called brushes, and they just they maintain contact with the commutator as to allow rotation but still conduct electricity. That's sort of their main job. But the commutator is the one that changes the direction of the current every 180 degrees to maintain a constant uniform direction of rotation. So some questions for thought. What is a torque at it? Sorry, where is torque at its maximum? So is the torque maximum here or some angle in between? Have a think about that. I think I jumped the slide, but the size of the torque is dependent on the magnetic field. So the stronger the magnetic field, the greater the force on the individual conductor, and so the greater the actual torque. And just by motor effect, the dimension, specifically the cross-sectional area of the coil, is important. And like, why is that important? Well, firstly, because if we have a longer part of the coil or a longer length of the coil within the magnetic field, we're going to have a greater force just by motor effect. But the reason that the entire area is important is because of if we draw the coil quickly. This is a top view of the coil. Now this length is important because that's the length that's within the magnetic field, right? The other length is also in the magnetic field, but it's perpendicular to the magnetic field. So, sorry, it's parallel to the magnetic field. So if the magnetic field is going something like that, it's parallel to the magnetic field, so it doesn't actually do anything if you think back to the motor effect and you think back to the right-hand rule. But the reason why this length here is important, so if I call this L1, the reason why L2 is important is because if L2 is greater, right, that increases the distance of this conductor from the center point. And remember, torque increases with greater distance from the center point. So the greater the distance from the center point, the greater the torque. And so the greater L2, the greater the torque. And so increasing L1, increasing L2 increases the actual torque. And so increasing the area, which is dependent on L1 and L2 increases the torque. The size of the current is important because, again, if you think back to motor effect, F equals to BIL sine theta. B, we talked about the magnetic field strength. Increasing that increases the torque. I is the current, so increasing the current increases the force on this individual conductor, thereby increasing the torque generated. The length we talked about because that's dependent on the area, or the area is dependent on the length. The number of turns in the coil is also important because real motors not only have just a single coil, they have a whole bunch of these coils all wrapped on top of each other. You would have 1, 2, 3, hundreds of coils, for example. And so increasing the number of turns increases the number of conductors that experiences a specific force, and so that in turn increases the torque. So the actual force on one side would be equal to BIL sine theta times the number of coils, because we have that many individual conductors within a magnetic field. The other thing that's important is the position of the coil on its rotation. So theta here is this angle in here. So if the coil is perfectly vertical, so I'm redrawing the setup here. Maybe I draw it on OneNote, sorry. I redraw the setup here. We have our north pole here. We have our south pole here. If we have our coil and it's perfectly vertical, right? This is a side-on view. If it's perfectly vertical, if you think about the current, it's actually going into the page, right? And this one's going out of the page. And so in that case, although we do have a force on each of these conductors, you'll see that since this distance from the center, this R, since the force is parallel to that lever, since it's parallel to that lever arm, so if I redraw that, this is our center, this is our lever arm, this is our force. Since the force is parallel to that lever arm, it actually generates no torque. So at this position, the torque is actually equal to 0. Whereas at this position where we've got North Pole and the South Pole and the coil being flat like so, and this is a point of rotation. Let's say we have the current going into the page here, out of the page here. If we have the force going up like this, would that be right? I think. No, sorry. Force would be by right hand rule. You would see the force is going down like this, up like this. What we would see here is that this distance here is perpendicular. The force is perfectly perpendicular to that distance, and therefore it's going to be having the maximum magnitude. So the torque is maximum at this position. So at some intermediate position, right, we're interested in what happens to that torque. Is it going to be greater? Well, I mean, I've said this is maximum, but what happens to that torque? Well, if we have something like this, we're interested in the perpendicular component of this force. So if this angle in here is theta, right, then we're interested in, and this force here is F, we're interested in F sine theta, the component perpendicular to it. So if I was to draw that on here, it's this component here. So now we've got this distance here, r. So we have F times r sine of the angle theta. So similarly, the torque is dependent on the sine of the angle theta. So at theta equals 0 degrees, torque is maximized. So that's this case here, right? And at theta equals 90 degrees, so the rotation becomes 90 degrees, torque is minimized. Sorry, other way around. Torque, in this case, theta equals 90 degrees, so torque is maximized, whereas in this case, theta equals to 0 degrees. Yep, get rid of that one. So at theta equals 0 degrees, we've got a maximum torque. Sorry, theta equals 0 degrees, we've got a minimum torque because the force is parallel to that lever arm. Whereas at theta equals 90 degrees, we've got a maximum force because the force is perpendicular to that lever arm. Maximum torque. So yeah, the size of that torque is therefore dependent on all these factors, and the actual magnitude of that torque is given by the formula. I'll let it load for a second. It's actually given by the formula torque equals to N being the number of coils, N times magnetic field strength times I being the current, A being the cross-sectional area, sine of the angle theta. Theta being the angle between the force. Yep, so you could think of theta being this angle in here, or you could think of theta being the angle between the force and the lever arm. Doesn't really matter because they're equivalent angles, so you could think of it as this angle here, theta, or you could think of it as this angle here, theta. They're both equivalent angles just by geometry, but yeah, just remember that it's dependent on sine of the angle theta. Make sure you get your angle theta right. So where is torque at its maximum? We talked about that when theta equals to 90 degrees, sine theta is maximized. Sine theta equals 1 because sine of 90 is 1, and so that would mean we've got the coil pretty much sitting perfectly flat or perfectly horizontal. So if there is no torque when the coil is perpendicular to the field, how and why does the motor keep spinning? Well, that's because of inertia, right? If we have something that's spinning and we don't apply a torque, it's going to continue spinning pretty much by Newton's first law, right? An object in motion tends to stay in motion. If you've got no resistive force, or if the resistive force is relatively small, it's going to continue spinning. So if there was no commutator to reverse the direction of the current and thus torque, what would happen? We talked about that. It would flicker back and forth because after doing one rotation, it would flip back and do like reverse because the direction of the current would now be opposite that, or like in the coil would be opposite that what it originally was. So is the torque that varies in size as the motor rotates good or bad, and how do we get rid of that? I'll let you guys think about that. Is it good or bad? Well, if we want to maintain a constant torque or we want to maintain a certain acceleration, we want to try and get a constant torque. How do we get rid of that? Well, we're going to have to sort of think about how we could position the magnetic field in such a way as to maintain a constant torque. Now, that is a bit beyond the syllabus as such, but it's still a good thing to research. Now, AC motors are practically identical to DC motors, except you don't need a split ring commutator. You have something called a slip ring commutator. And all that does is it maintains contact with the rotor. And the reason why we don't need a split ring commutator is because when we're talking about DC current, it's something like that. It's always positive, right? So this is, let's say, voltage over time. This is DC. But in the case of AC, if we're looking at the voltage over time, it's actually going to flicker back and forth. It's going to flick up, down, and so. It's actually sort of like a sine wave. It is a sine wave, pretty much. So AC current sort of flickers back and forth, positive and negative, and as a result, it causes and as a result, we don't actually need a split ring commutator. If it rotates 180 degrees and then the current itself flips direction, it's going to maintain that constant rotation, that constant direction of rotation. So all that's required is to maintain contact with this coil while it's rotating. So yeah, that's what AC slip ring motors look like. Now there are another class of motors called AC induction motors, and we'll talk about that in a bit. But for now, let's jump into something called back EMF. So back EMF is something that's induced. So back EMF is an induced current that opposes current flowing through a coil. So remember when we talked about EMF and Lenz's law and that sort of thing, we talked about how if we have a coil which experiences a changing flux, it's going to experience a change in. It's going to induce a current within that coil. So if we have a north pole, maybe I'll fix that. So let's look at an example. We've got a north pole here and south pole here. So as the supplied current goes in this direction, right? What happens is when this coil rotates, it's actually continuously experiencing a change of flux. Although the conductor is experiencing a force and it's rotating because of the motor effect, as a result of Lenz's law, the coil itself is still experiencing a change in flux. And so because it's experiencing a change in flux, it wants to try and oppose that change in flux by generating a current which opposes that. So we're going to have current which opposes the induced current. Which opposes the applied current. So we're going to have an induced current, which is the blue one. And we're going to have an applied current, which is the red one. And so we're going to have a net lower current. So what the back EMF is that induced voltage which opposes the supplied voltage as a result of Lenz's law. So basically it stops the motor from whizzing off to infinity because of the fact that when you've got a greater and greater angular velocity, you're going to have a greater and greater back EMF, and so you're going to have a lower net voltage, and so that's going to stop it from having infinitely large velocity. Now, coming into generators, we've got generators are exactly as important as you think they are, whereas motors rely on the motor effect, generators rely on electromagnetic induction, so that's like Faraday's law or Lenz's law that we've been talking about. So in this case, in the case of motors, we don't really like back EMF because it slows it down because it opposes the supplied voltage. But in the case of generators, we're completely relying on back EMF. It's not quite called back EMF in generators, but the phenomenon is exactly the same. So when you spin a coil in the magnetic field, by Lenz's or Faraday's law, you've got a current that will be induced in the opposite direction of motion, and so boom, you've made electricity. So what that means is that in the case of motors, we're supplying it with a current and it's rotating, and because it's rotating, it experiences a change in flux, and so it's got an opposing voltage. But what happens if we go by hand and crank it or use a turbine or something to spin this coil within a magnetic field? Well, in that case, we've got no supplied voltage, but we're going to have an induced voltage, and that induced voltage is going to cause a current to flow, and there we have electricity formed. So generators, we have a flow of current, so electricity. So we have generators, right, which take mechanical energy. So we're spinning that crank, or we're using a turbine to spin that generator. And within that generator, we've got a coil, and that coil is rotating within a magnetic field, and therefore we're going to have electricity, right? We're going to have an induced current. So generators, very important because they are utilized to generate electricity. So whether that be through renewable sources, so when you've got other than solar, but when you've got a wind, when you've got wind turbines, wind energy, or when you've got hydroelectricity where you're relying on the flow of water to rotate that turbine, and then you use your generator, which has the coil rotating with a magnetic field, generating electricity, generating current, or in the case of even non-renewable fuel sources, when you're relying on steam, or when you're relying on coal, which heats up liquid, so steam, and therefore uses that steam to generate electricity by using a turbine, and so on. So generators is very important. An AC or a DC generator is practically identical in construction to its motor counterparts. So motors, remember, they take electrical energy supplied from an external circuit, whereas generators, they supply electrical energy to an external circuit by using energy from other outside means. So it's some sort of mechanical energy. So motors take electrical energy, turn it into mechanical. So they take that supplied voltage, rotate because of the motor effect, whereas generators, take mechanical energy in the form of rotation from wind turbines or whatnot, and they turn it into electrical energy. So the current supplied to the rotor produces a force by motor effect, which causes rotation in motors, whereas in generators, the rotor is spun by some sort of external source of energy, like I said, steam, water, etc., or wind or whatnot, and that causes the coil within that generator to spin within that magnetic field, but which by Lenz's law or by Faraday's law causes a induced current, so induction. Now, AC generators, they're much easier to construct. They've got less wear on parts and can be transformed, but they are less safe. Whereas DC generators, they're more usable, energy or power per volt, and they degrade, but they do have parts that degrade more quickly, and they cannot be transformed. Because remember, transformers rely on AC current, or the properties of AC current of a changing magnetic field, whereas DC does not supply that. Now, it almost appears that though DC generators would be superior, but the ability to be transformed is a very big deal. And remember how we talked about how important transformers were. So let's look at one more application of induction, and that's AC induction motors. So remember we talked about slip ring AC motors. This is another type of AC motor, but these are way more efficient, way more commonly used in sort of large-scale machinery and all that sort of stuff. So AC induction motors, and as the name suggests, it works by induction. It's completely different to a normal motor, but the rotor is separated from the external circuit. So what that means is if you have a magnet, right, and you have a rotor, and you start rotating this magnet around, what happens is we've got a magnetic field, and let's say we have a singular magnet and we rotate it around a rotor. It actually starts following that because of Lenz's law. This rotor experiences a change in flux in this region, and that generates a magnetic field to oppose that. And by as suggested by Lenz's law. And so as we move the magnet around the rotor, it actually follows it. So it removes the relative motion between the two objects. So we've got a change in flux experience, and so as a result of change in flux, we've got a magnetic field. We've got a current induced within the rotor, and that interacts with this magnet as to oppose that change in flux. So it starts following that magnet, and so it starts rotating in the same direction. So AC motors pretty much make use of this phenomenon. So AC induction motors, they consist of a squirrel cage rotor and three sets of stators, stator magnets at 120 degrees from each other, and an axle. So there are something called phases. So you've got different phases for the current, and it's sort of related to when you think about sine waves and you're moving them side to side, you've got a phase shift, very much related. But what that means is we're going to start with a magnetic field here, and then this is going to sort of turn off or reduce in magnitude, and this magnetic field here is going to increase, and then it's sort of going to turn off, and then this one is going to increase and then turn off. This one's going to increase, turn off, and so on. So what it looks like to the squirrel cage rotor is that we're going to have a magnet that's sort of moving around. So this phase difference between these three sets of stator magnets is gonna in the case of the squirrel cage rotor, it's going to look like a rotating magnetic field. And because of that rotating magnetic field, by Lenz's law, just like when we have a singular magnet, it's going to try and oppose that change in flux by rotating alongside the rotating magnetic field. So it's going to rotate in this direction. So as the three-phase AC current creates a rotating magnetic field, so we have a north. We have a north here and then a south here generated. And then when we turn that off, right, we're gonna have a north here and a south here generated. Turn that off, then we're gonna have a north here, south here generated. Turn that off, and keep going around and around and around. So when I mean off is because of the nature of AC, which is sort of a cycle. We're gonna have a maximum, and we're gonna go to pretty much zero. So that's what I mean by off. And then it's gonna pick back up, or like the magnitude is gonna increase, but the actual direction of the current is in the opposite direction, and so it looks like a rotating magnetic field, and that causes this squirrel cage rotor to also rotate along with it as a result of Lenz's law, which is trying to resist that change in flux. And that's how a three-phase induction motor works. So yeah, that's pretty much it for today. I think I'll leave the last maybe 4 or 5 minutes to questions in the chat. But yeah, I think that's all we have for today. Thank you guys.